In mini lecture 34, we introduced the average power, which some folks call the real power for sinusoidal circuit, for AC circuits that operate in steady state at one frequency, that are on for a long time with all of the criteria that AC circuits and steady state circuit meet. So we introduced the average power. The average power is the power that your light bulb, the 60 watts light bulb, it is the power that often customers are charged for devices that are consuming power. So it's really probably the most important power. But we also introduced some really important power concept. We introduced the power factor, which essentially it's a relationship between the angle of the voltage and that of the current. It tells you how out of phase the voltage and current are. In essence, telling you how capacitive or inductive a circuit is. So if essentially the circuit is purely resistive, then the voltage and current is going to have the same angle. And if the voltage essentially is purely inductive or purely capacitive, the angle is going to be 90 degrees. So the cosine, the power factor will be 0. So the power factor is really important, and you got to get a little bit used to classify it as lagging or leading, depending on the relationship between the voltage angle and the current angle. We also introduced the apparent power in volt ampere. Apparent power is kind of what you think you're delivering to a circuit. That's what we call it, apparent power, essentially. So today we're going to look at the complex power that has everything in it. In my view, the complex power is the quintessential power calculations for AC circuit. I recommend to students to always go to the complex power, regardless of what you're being asked, because any question you can ask can be found from the complex power. So it's kind of almost a security blanket in terms of how we answer power questions for sinusoidal circuits. So let's share the slides here. So again, anytime we discuss power, we are talking about a circuit that has been solved. Okay, we've solved the circuit, nodal, mesh, other methods that we've seen in the past. So we saw this. So we start this discussion of power by looking at a particular passive circuit or element, but let's look at a passive circuit. And the reason I know that it's passive because my current is entering the positive terminal. So if it was a source, I would be essentially having the current entering the negative terminal of the voltage. Okay, so we start this by looking at a passive circuit. And we're going to flat out define. So for this particular circuit in phasor, we assume that the current is some magnitude Im, some angle phi, something you've seen in the past. I've used that nomenclature, that notation for current before. And the voltage across that passive circuit has a magnitude Vm and an angle theta. We're going to define the complex power as 1/2 the phasor voltage multiplied by the conjugate of the phasor current. You may not remember, but when we find the conjugate of a complex number by simply changing either the sign of the imaginary part, the sign of the J, or changing the sign of the angle. Either way, so we can come up with the complex number of that. So if we do that, given these current and voltage across this passive element, the complex power, and you need to know this, it's 1/2 Vm, the magnitude of the voltage, Im, the magnitude of the current, and the phase angle is the angle of the voltage minus the angle of the current. The minus sign comes from the conjugate of the complex phasor. Okay, so what I'd like to tell students is the best thing to do when you calculate the complex power is to write it in rectangular form and in polar form. So obviously, what I'm pointing with my arrow here is the complex number in polar form, magnitude and phase. If you write the complex number in rectangular form, you're going to have the real power, the real part of the complex number. If you write the complex power in rectangular form, you're going to find that the average power is the real part of the complex power. So the average power here is 1/2 Vm Im cosine theta minus phi. Okay, so that's the average power is the real part of the complex power, and it's in watts. So the average power that we had before. So we're introducing a new also we are introducing a new power here today. Beside the complex power, we're going to introduce the so-called reactive power, which is the imaginary part of the complex power. The imaginary part of the complex power, we call it Q. Each unit's going to be volt ampere reactive. What it is essentially, it's a measure of how much average energy is in those inductor and capacitor that make up that load. Okay. So by looking at the sign of Q, we can determine whether we're dealing with an inductive load and a capacitive load. Okay, so those are the things that, and now I'll do a little summary before we end here in terms of what you need to know from a sinusoidal power point of view. Okay, so again, just as a recap, we defined the complex power today, that's our definition here, as 1/2 the phasor voltage times the phasor current conjugate. Remember how to get the conjugate of a phasor. Okay, we'll change either the sign of the angle or the sign of the imaginary part. Either one does that. We also realize that the average power is actually the real part of that complex power in watts. And of course, today we're introducing a new power called the reactive power in VARs, and that's the imaginary part of the complex power. And simply looking at the sign of Q tell us whether we're dealing with an inductive load if it's positive or a negative load if it's negative. Finally, the apparent power, which we had seen before, it's the magnitude of the complex power, 1/2 Vm times Im. That's the apparent power in volt ampere. So you can see how the complex power has all the parts that we essentially has, and the complex power in polar form, pretty clearly, you can access the power factor from the phase angle by taking the cosine of that phase angle. So everything is in there in the complex power, okay? All right, so let's look at a basic example to cap up this mini lecture here on complex power. We're essentially saying, okay, for this circuit, this has a sinusoidal waveform here operating at 1,000 radians per second. So essentially that source is 15 square root of 2 cosine 1,000 t. That's what that means when I say that. And then it's connected to a load, and the load is made up of resistors, inductors, and capacitors given by these values here. And you're being asked to calculate the average power dissipated by the load and the power factor that the source is seeing. Okay, so I'm hoping at this point you can answer with a measure of confidence that the average power that the 10 millihenry inductor dissipate is 0. The same thing for the capacitor, because these are purely reactive element, and we've actually convinced you that if you have a pure a pure inductor or a pure capacitor, the average power dissipated is 0. But we'll show that in essence here. So let's convert this circuit to phasor form, since we have the frequency of 1,000 radians per second. So we calculate the impedance of the capacitor and the impedance of the inductor. And the source essentially in phasor form is 15 square root of 2 at an angle 0. So I could do nodal, I could do mesh here, but I can also just simply combine impedances here. Okay, I can combine impedances here and solve. So in essence here, if I focus on this source here, I have the voltage, all I need is the current. If I need the current, I can answer the complex power question, 1/2 phasor voltage times phasor current conjugate, okay? So I'm seeking to calculate, again, I can combine the impedances, just that complex resistances, that's the nice feature of phasor. So the 10 ohm is in parallel with the series combination of the capacitor and the inductor impedance. Okay, and then the current then becomes voltage divided by the sum of the equivalent impedance, essentially. So we get a current to be 3 at an angle 45 degrees. Okay, so now I have the current, I have the phasor voltage. I can probably calculate the complex power supply. It's 1/2 V times I conjugate. So you see V at an angle 0. Okay, the current at an angle 45, so I change the 45 to minus 45, and I simply calculate the complex power. And the complex power, again, I'm encouraging you to write the complex power both in polar and in rectangular form. In polar form is 31.82 at an angle minus 45. And if I convert to rectangular, it's 22.5 minus J 22.5. So this is the average power, okay? This minus 22.5 is the reactive power in VARs. So the average power is in watts. Okay. The apparent power here is what I'm circling here in volt ampere is 31.82. It's the magnitude of the complex power. And if I wanted the power factor, I would just take the cosine of the minus 45 degree. That would be the power factor. Okay. And I can see that essentially I can determine whether it's lagging, leading, and what have you. Okay. So this is obviously a capacitive circuit because Q is negative. So I can also give that statement to that effect. Okay. So, but again, we've calculated so we can again say that the apparent power is 31.82 volt ampere. The power factor is cosine of that phase angle of the complex power. And then I can state that it is leading because the angle of the current is ahead of the angle of the voltage. Okay. So all of those things are in the complex power. All right. And from then on, I can also say the average power dissipated is 22.5. And I can even conclude that 22.5 is all going to be dissipated by this because the inductor and the capacitor on average dissipate no power. Okay. All right. So that kind of concludes this particular example here. I'm going to go onto the document camera just to do a little recap of the complex power, putting all those things in one place for you to have. Just give me a second here. So what we're looking at here, we're looking at some passive circuit. Okay. Some passive circuit here. It has a current here, which we've been saying IM at an angle phi. And it has a voltage across it in phasor Vm at an angle theta. Obviously, we're solving this circuit using the phasor method here. And what we've essentially been saying that the complex power is the most complete power definition. Defined as S. And we define it as 1/2 voltage current conjugate. So if we put this essentially, so this being the current and this being the voltage. So if we substitute this, we have 1/2 Vm Im, and then we got the phase angle of the voltage, and then we're going to pick up a minus sign here, so it's going to be theta minus phi. Okay, so that is the complex power in polar form. So this is the complex power in polar form. So in polar form, we pick up very easily. We pick up the apparent power. Which is the magnitude of the complex power, 1/2 Vm over Im. We can easily pick up the power factor from taking the cosine of the phase angle. So we pick up the power factor as cosine theta minus phi. Okay. All right. And of course, we can determine whether it's leading or lagging by simply looking at the phase angle here. Okay, if we look at the phase angle here, if the phase angle is positive, it's lagging. If the phase angle is negative, it's leading. Okay, so a lot of information on in the complex power in polar form. If we convert it to rectangular form, S is equal to 1/2 Vm Im cosine theta minus phi plus J 1/2 Vm Im sine theta minus phi. Okay, so that's the complex power in rectangular form. This is the complex power in polar form here. This is the average power in watts. And this is the reactive power Q in VARs, voltage ampere reactive. Okay. All right. We can say if Q is positive, the circuit is inductive. If Q is negative, the circuit is capacitive. Okay. So this is a good summary of why the complex power, it's all included. So when you're being asked power, you might think of finding in essence, all you need to find the complex power is the voltage and phasor. Of course, realize that if this particular circuit has an impedance, we can voltage over current is some impedance here. So this becomes essentially Vm over Im. What's the angle of the voltage minus phi equal the impedance of the circuit? Okay, so depending on how you're being phrased the problem, that's also very important to see that. But this is actually a good summary of how the complex power gives you all the information you need that I could be asking you for a particular power consumption by either a circuit element or a portion of the circuit. Hope that helps.